This presentation is meant to overcome a big problem having to do with the weatherization of existing buildings. First, the problem. I've always thought of air sealing as a distinct weatherization measure, and I've always thought of installing ventilation as a distinct weatherization measure. Air sealing saves energy and increases thermal comfort. Installing ventilation is a health and safety activity that does not save energy, but increases energy use, although slightly. For the last decade or more, I've been frustrated by my inability to convince people that it's a good idea to air seal a house and then install ventilation. For many people, it seems that these two measures are working against one another, or that one undermines the other. How do we find a way around this conceptual problem? The solution? What if, rather than thinking about air sealing and adding ventilation as two distinct measures, we think of them as two parts of one measure? What if we call this measure taking control of airflow, or simply controlling airflow? The first task of this controlling airflow measure is air sealing. Air sealing reduces uncontrolled air leakage. The second task of the controlling airflow measure is installing ventilation according to ASHRAE 62.2 to ensure a controlled amount of fresh air from the outdoors. These two tasks go hand in hand as the two parts of controlling airflow. One is not appropriate without the other. In this conceptual frame, air sealing and ventilation are no longer battling one another as two distinct, conceptually opposed measures. It's possible that this idea might foster buy-in from installers and homeowners. Taking this idea a bit further, perhaps we should not look at the benefits of air sealing alone, but look at the benefits of controlling airflow. The benefits of controlling airflow are, number one, reduced energy loss from air leakage. Number two, increased thermal comfort. 3, enhanced health. And 4, lower medical bills. The costs of controlling airflow are 1, labor and materials for air sealing, and 2, the cost of installing ventilation fans and controls. The SIR of controlling airflow can be calculated in this manner. In the next few minutes, I will explain how to do this using a few free online tools. On the next slide coming up, you will see the savings to investment ratio equation put together especially for doing this calculation. There'll be a number of new things in there that you want to take note of. You might want to get ready to take some notes. Of course, you can also pause this video at any time and write things down, or go back over them, or reverse it, whatever you wish. At the top of this slide is the basic savings to investment ratio equation. The savings the first year over the cost times the life of the measure. With that in mind, what we've done here is add a number of things to this so we can look at the savings to investment ratio of controlling airflow. First of all, in the more complex equation, therm sub AS is the therm load reduction from air sealing minus the therm load increase from the ventilation. All of that is times the dollar per therm. You'll see how that's calculated. Minus the electrical use of the fan, which we can calculate, plus lower medical costs, LL, longer lifetime, EQL, enhanced quality of life, times the life of the measure. Then in the denominator is the cost for air sealing plus the cost of ventilation system installation. Everything is included here. Take some time to look over this equation more carefully. Something that's important to figure out for calculating the savings to investment ratio is the savings from the air sealing. To do that, we're using the advanced infiltration tool at residentialenergydynamics.com. We are starting with a building leakage of 3,000, and as you can see in the text box that's added to it, we are tightening it to 1,800 CFM50. In another part of this tool that I'll show to you, you can see by what amount that reduces the load of this building that's in Portland, Maine. It's a house in Portland, Maine, using that climate data for this analysis. Look over this tool and go to the website and give it a try if you wish. This slide shows, again, the advanced infiltration tool at residentialenergydynamics.com. For the tool on the left, the CFM50 before tightening is 3,000, and the corresponding heating load, highlighted in yellow further down in the tool on the left, is 276 therms. The tool on the right is the tightened house, 1,800 CFM50, and further down, highlighted in yellow, the heating load is 165 therms per year. The difference between the pre and the post load in therms for heating is 111 therms, as you can see in the green text box in the middle of the slide. If you're interested, you can look further down on each of the tools, the left and the right, and see what the cooling load is before and after air sealing. This house is in Portland, Maine. Not much of a cooling load. Here we have the Residential Energy Dynamics ventilation tool, ASHRAE 62.2 2013 version, showing the ventilation rate for a whole building ventilation, it's highlighted in yellow, of 34 CFM running continuously. This tool is split into parts so that you can see all of its sections on the slide. There's one section, the very bottom section, that you can't see. Again, this is for Portland, Maine. It's an existing home of 2,400 square feet, 4 occupants, and 2 stories. The measured leakage, again, is 1,800 CFM50. This is another piece of information that we need to calculate the savings to investment ratio for controlling airflow. We need this because we need to know the cost of operating this ventilation, both the electrical cost for the motor and the additional load imposed by this unbalanced ventilation. In this slide, we are back to the advanced infiltration tool from Residential Energy Dynamics, and we have entered on this tool the unbalanced ventilation rate that we showed on the previous slide from the ASHRAE 62 2013 tool of 34 CFM. Assume this is an exhaust fan running continuously. You can see that in the top yellow highlight. Below that, you can see the date range. Notice that the date range is for the entire year, and the highlight at the bottom of the tool is the increased load due to the operation of this ventilation, which is 6.4 therms for the year. Again, this house is in Portland, Maine, where it's pretty cold, and this shows us the increased load due to ventilation. The next thing we are going to calculate is the electrical power usage or cost for operation of this fan all year long. Here is the RED Calc free ventilation electrical usage tool. We're going to use this to calculate the annual electric cost for operating the ventilation fan. This tool can be used for operating anything, a light bulb, a stereo, anything you wish, but here we're going to use it for ventilation. We're assuming the power rating of the fan is 20 watts. We're assuming it's going to run 300 days per year, probably off much of the time in the summertime. The hours for each of those days will be 24 hours, 60 minutes for each hour, and the electrical cost in Portland, Maine is about 14 cents per kilowatt hour. So we have the results at the bottom of the tool. The annual usage time is 7,200 hours. The annual usage is 144 kilowatt hours, and the annual electrical cost, quite low for operating this fan 300 days per year, is $20.20. That's highlighted in yellow right at the bottom of the tool. I have already mentioned a number of times the therms saved and the therms utilized for ventilation. So we need to know the cost per therm. The equation at the top of this slide shows the cost per therm. It's equal to the cost per unit times 100,000 over the BTUs per unit times the efficiency expressed as a decimal. For this house in Portland, Maine, we're using oil, number 2 oil at $3.60 per gallon, and we're assuming an 85% seasonal efficiency of the system. So we've got $3.60 as the cost per unit times 100,000 over 140,000 BTUs per unit for number 2 oil times 85% efficiency. When you work out the math, you get a cost per therm, this is usable therm within the home, of $3.11. If you're calculating this in your area, you will have different figures to put into this equation, and you'll get a different result. This is the second time you've seen this equation. It's the savings to investment ratio equation for controlling airflow. The simple SIR equation is at the top of the slide, and then the customized one for controlling airflow is in the middle of the slide. Starting over at the left with the numerator above the line, we have the therm load reduction from air sealing. We subtract from that the therm load increase from the ventilation system. Then we multiply that result times the cost per therm, which we just calculated on the previous slide. From that, we subtract the electrical cost to run the fan for 300 days. Then after that, we have 3 health values. We're going to set all of these to 0, but they might not be 0. LMC is lower medical costs, LL is longer lifetime, and EQL is enhanced quality of life. Then way over to the right is the life of the energy saving measures, in this case the air sealing materials we put in and the ventilation system. Then in the denominator we have the all-important air sealing cost to go from 3,000 CFM50 down to 1,800 CFM50, and We add to that the cost of installing the ventilation system. Here you see that we have entered values for the SIR equation for controlling airflow. In the third equation down, we've got the therm load reduction from air sealing of 111 minus the therm load increase from the ventilation system, 6, times $3.11 per therm minus $20 for operating the fan for 300 days. I've rounded that from $20.20 to $20. And then for the health variables, I've set those all to 0 just to show that even without considering enhanced health, and there are indeed studies that show that ventilation does enhance health, I've set those all to 0 just to show that we can get an SIR greater than 1 without those. And then assuming 15 years for the life of the air sealing in the ventilation system. In the denominator, $3,000 for air sealing to take the house in Portland, Maine from 3,000 CFM50 to 1,800 CFM50, and then add to that the cost of installing the ventilation system, in this case an exhaust fan with controls, a good exhaust fan with controls, $600. The SIR is equal to 1.3. If we have an SIR greater than 1, we're in good shape. This means for every dollar we invest, we get $1.30 back. To arrive at this equation and to get these variables, we've used 3 RED Calc free tools. The advanced infiltration tool has been used a number of times. The ASHRAE 62.2 2013 tool has been used as the ventilation, and the ventilation electrical usage tool has been used to calculate the cost of running the ventilation fan, the electrical cost. We've also used a cost per therm equation to figure out the cost per therm in Portland, Maine. On the previous slide I mentioned the health values in the numerator of the savings to investment equation. These are LMC for lower medical costs, LL for a longer lifetime, and EQL for enhanced quality of life. It's very difficult to quantify these, and research is just beginning to get a grasp on how to do so. So as I mentioned in the previous slide, I set these to 0 and showed that the savings to investment ratio, even in such a case, can be greater than 1. These values can or could be very large, and if so, they would significantly increase the savings to investment ratio value. This little demonstration has shown that controlling airflow can be cost effective from the standpoint of the savings to investment ratio, even without including health benefits. This is a significant step forward. This is a different way of looking at ventilation as part of controlling airflow. The first step of controlling airflow being air sealing, that is tightening a house. The second step of controlling airflow being putting in mechanical ventilation to bring in a proper amount of air. Not too much, not too little, but just right. There's a greater likelihood of this being cost effective, or in other words, the savings to investment ratio being greater than 1 if significant air sealing is accomplished. Number 2, if the cost of air sealing is low per CFM50 reduction. Number 3, if the cost of the ventilation system installation is low. 4th, if the cost of heating and cooling energy is high. And finally, if the electrical cost of operating the ventilation fan is low. I encourage you to use the RED Calc tools and the savings to investment ratio in this presentation and give it a try. See if some of your jobs of controlling airflow are cost effective from the standpoint of a savings to investment ratio greater than 1. As a partial review, I want to just remind you of the RED Calc free tools that were used to demonstrate how to calculate the savings to investment ratio for controlling airflow. The first was the advanced infiltration tool, and we used that to calculate the load reduction for air sealing. We did it for heating only, but the tool will also give it to you for cooling. We used the advanced infiltration tool, one more time for determining the increased load as a result of operating the ventilation system. Again, the tool will give you that value for heating and cooling, but we only looked at it for heating because our example was in Portland, Maine, which is primarily a heating climate. The second tool we used was the ASHRAE 622-2013 tool. We use this for calculating the ventilation of the Tightened house, 1800 CFM 50. That value for whole building ventilation came to 34 CFM. And finally, we use the ventilation electrical usage tool for calculating the cost of operating the fan motor for 300 days per year. You could use 365 or fewer, whatever you wished. If you would like more information about these tools or other tools, please visit www.residentialenergydynamics.com.